Welcome to the Chapter 5 Part 3 video. This covers 5.4 and 5.5. 5.4, I'm just going to show you some additional identities and prove one of them, but the majority of this video will be focused on the law of signs, which is 5.5. So we're going to do a brief view of the double angle, power reducing, and half angle identities. Then we're going to derive the law of signs, look at solving triangles using angle, angle, side, or angle, side angles. And then an ambiguous case, meaning that there could be two possible triangles when we're given a side, side, and angle. And then if we have time, we'll look at an application. Why is this important? The multiple angle identities, those are the identities that I'm just going to show you very briefly, are useful particularly in physics. They're not particularly useful to memorize all of, but being able to recognize them is always helpful. And then the law of signs is a powerful extension of the triangle congruence theorems that you might remember from geometry. So on this screen, I have all of those identities that we mentioned. The double angle identity, notice the angle here is 2u. So that's why it's a double angle. It's sine of something that has been doubled, cosine of 2u, tangent of 2u. And this is what we're going to derive on the next slide. We're going to prove the first one, and then I'll show you how you use that to get the other two. And then the power reducing identities comes directly from these identities of cosine. You can solve for sine to get the first one, solve for cosine to get the second one, and then using that ratio to get the last one. And then we have our half angle identities. These, again, come from those double angle identities, which come from, as we'll see on the next slide, the sum and difference identities. Okay, so all of these are relating back. There are simpler forms of these identities in the sum and difference identities, but these are specific if you're trying to use double angle, half angle, or power reducing. Notice this starts with a sine squared and we end up with nothing squared. So that's why it's a power reducing identity. So let's go ahead and prove a double angle identity coming directly from the sum or difference formulas. So if I'm looking at cosine of 2x, I can write that as cosine of x plus x. Cosine, the cosines go together like cosining Elise. So I get cosine of x times cosine of x. Since the cosines stay together, the positive and negativeness of our sign here switches. So positive becomes negative. And then our signs are together. And a simplified way of writing that, cosine times cosine is cosine squared. So this becomes cosine squared x minus sine squared x. That's our first identity for cosine of 2x. Now, using the Pythagorean identity, we can derive the other two. So if I replace sine squared x with 1 minus cosine squared x, I find that cosine squared x minus, in parentheses, 1 minus cosine squared x equals cosine squared x minus 1 plus cosine squared x, leaving me 2 times cosine squared x minus 1. And that is equal to cosine of 2x. If you wanted to derive the power reducing identity, you could solve here for cosine squared x and get that power reducing identity. We're going to take that intermediate answer that we got, the first identity that we derived or proved, and we're going to go ahead and replace, instead of sine squared, the cosine squared x from the Pythagorean identity. And we're going to follow the same process. So now we have cosine of 2x equals, instead of cosine squared, I'm going to write it as 1 minus sine squared x minus sine squared x. Nothing to distribute this time. It's just 1 minus 2 sine squared x. And then again, if you solve for sine squared of x, you will get the power reducing identity directly from here. Okay, so this is just showing you that there's not only the basic identities that we looked at the first day, And then we had a new set of identities, the sum and difference identities. Now those ones are harder to derive, but they're useful in getting even more identities, such as the double angle, half angle, and power reducing identities. Okay, so just a little bit of an introduction to that. We're not going to go into more detail than that. I want to keep on moving forward with the law of signs. Now, the law of signs is really, really useful because now we don't have to have a right triangle. Everything, remember, in geometry, using trigonometric functions, we always had to have a right triangle until we got to the law of signs. So you might have seen this before in geometry. If not, I'm going to show you how we get this law and then how to use it. So the first thing that I'm going to do is taking this triangle, I'm going to draw an altitude. Altitude is perpendicular to one side that goes to the opposite vertex. So I'm drawing the altitude of side C. And what that does is it creates these two right triangles. And I'm going to set up two equations. The first equation that I'm going to set up is for angle A. Sine of angle A, that's opposite over hypotenuse. So we need a name for this altitude here. I'm going to call it H1. And we'll see why, because I'm going to do another altitude in a few minutes that we'll call H2. So opposite of angle A is H1, divided by the hypotenuse of this triangle is side B. Let me do that in the same font. And then if I isolate H1, so multiply both sides by B, I find that H1 equals B times sine of A. We're going to do the same thing for angle B. So angle B, take sine of angle B equals opposite, that's H1 again, over hypotenuse. The hypotenuse of that right triangle is A. Isolating H1 equals A times sine of B. Now I can substitute H1. So I get that A times sine of B equals B times sine of A. Divide both sides by AB. Reduce. We get sine of angle B divided by side length B equals sine of angle A divided by side length, A. Okay, I'm going to write that up here. Sine of B over B equals sine of A over A. The reason I'm going to do that is because I'm going to reuse this triangle with a different altitude now to find our last part of the law of signs. There we go. So the new altitude, and I could have done either one, either of the other two altitudes, but we really only have to do it one more time. So now I'm going to use angle A and angle C. We'll start back. Now I'm going to call this H2. So we have sine of angle A equals opposite over hypotenuse. So then H2 equals C times sine of A. Do the same thing for angle C. So sine of angle C, opposite is H2 over the hypotenuse of that right triangle is A. Then H2 equals A times sine of C. Substitute H2. So then we get C times sine of A equals A times sine of C. Divide by AC. Then we get sine of A over A equals sine of C over C. Okay, well, this is the same triangle. So this A is the same in what we found first and what we found second. and angle A is the same. So I can actually extend my equation up at the top to include the ratio of sine of angle C divided by side length C. And that is the law of sines. So the law of sines states that in triangle ABC, and it doesn't have to be a right triangle, if the angles are called A, B, and C, and the opposite sides, so angle A is opposite side A, angle C is opposite side C, and angle B is opposite side B, the following equation is true. Sine of A divided by A equals sine of B divided by B equals sine of C divided by C. I can also say, because of properties of proportions, that A divided by sine of A equals B divided by sine of angle B equals C divided by sine of angle C. Okay, so if I'm solving for an angle measurement, this is going to be more helpful because the angle is in the numerator. It's going to be easier to solve for. If I'm solving for a side length, this second set of proportions will be a little bit easier to use. Now, no matter which one you use, you'll find the right answer. But if you use the first one, you fall into that risk of saying something like, if I had sine of 37 degrees divided by 14 equals sine of 40 degrees over x, sometimes we fall into this trap of dividing both sides by sine of 40 degrees and then thinking that that x automatically becomes a numerator because the numerator is gone now. But really, this is sine of 37 degrees divided by sine of 40 degrees times 14 equals 1 over x. And so if you use this second set of ratios, second set of proportions there down at the bottom, then you are less likely to fall into that trap. So let's look at an example. In this example, we have two angles given and one side. And whenever we're given two angles and one side, we can finish solving this triangle. To solve a triangle, just like it was in geometry, that means I want to find all 6 values of the triangle. That is 3 angles and 3 side lengths. The capital letters always mean the angles. The lowercase letters always mean the side lengths. So I'm going to draw a triangle. And again, this is a sketch. It's not to scale. A, B, C. Angle A is 38 degrees. Angle B is 46 degrees. So I can already fill those two in. Side length A is 9. Side length A is always opposite angle A. So we have the side length between vertex B and vertex C is 9. Okay, so I need to find the rest of them. The first thing I can do here, I have 2 angles. I can always find the third angle using the triangle sum theorem, which says that all 3 angles of a triangle add up to 180 degrees. So angle C is 180 minus 38 minus 46. And if you try that in your calculator, you should find that that gives you an angle of 96 degrees. Okay, now we need to find the side lengths. Since I'm given both angle A and side length A, that tells me that's the ratio that I want to use. It's going to be sine of angle A divided by side A, and that's what I'm going to use to find the other 2 side lengths. I usually start by using the other angle that was given arbitrarily. It doesn't really matter. So I'm going to find side B first. Since I'm looking for the side length, I'm going to put the side length in the numerator divided by sine of B equals A divided by sine of A. B is my unknown. Sine of angle B, sine of 46 degrees. Make sure your calculator is in degree mode. Side length A is 9 divided by sine of angle A is 38 degrees. Then B equals, multiply both sides by sine of 46 degrees. 9 times sine of 46 degrees divided by sine of 38 degrees. Try that into your calculator. You should get that it is approximately 10.516. No units are given, so we leave it at that. And then lastly, we need to find our last side, which is C. Again, I'm going to use the given ratio. I'm going to use A. I'm going to use A and C because now I'm looking for C. So I'm going to say C divided by sine of angle C, which is 96 degrees, equals A divided by sine of A. Multiply both sides by sine of 96 degrees. C equals 9 times sine of 96 degrees divided by sine of 38 degrees. And that should give us 14.538. Again, no units given, so 14.538 finishes our triangle. 3 angles and 3 sides. Okay, now if I'm given 2 angles and a side, this will always work. But sometimes we can be given 1 angle and 2 sides, and then it gets a little bit more complicated. So let's look at a case. This is called the ambiguous case, when I'm given 1 angle and 2 sides. And the reason that this is ambiguous is because if I try to draw a picture of this, let's start with side A is between vertex B and C. So I'm going to start between vertex B and C is a length of 12. Okay. I also know that angle C is 25 degrees. So I can construct an angle here that's 25 degrees. And I know that some point along that angle will be vertex A. I also know that side C is 8 units long. Side C is going to go right here attached to B, and this is going to be 8 units long. So if I sketch this, think about using like a compass that's 8 units long, right? Then there's actually 2 places that I can put vertex A. And that's what it means by the ambiguous case. It means I don't have enough information to say what the triangle definitely looks like. There could be 2 options for this triangle. Okay, so we're going to have 2 different triangles that we look at. Here is triangle ABC. We'll call this triangle 1. So A1, B1, C1. And then we also have the option of this obtuse triangle ABC, and we're going to call this triangle 2. Okay, we know that angle C is 25 degrees. That hasn't changed. We know that side A is 12 units long. That hasn't changed. And we know that side B is 8 units long. That hasn't changed. I'm going to go ahead and draw this a little bit further away. I think that will make it a little bit easier. This was C2. A1, B1, C1, 8 units, 12 units, 25 degrees. Okay. So we have our 2 possible triangles. Now we're going to use law of sines on both of those triangles and solve them both. Okay. So first I'm going to start out with, I know side A and side C. So let's find our missing angle A. So we're going to go, this is triangle 1. I'm looking for the angle, so I'm going to put sine of angle A divided by side A equals sine of angle C divided by side length C. So then I have sine of angle A equals, multiply by 12 on both sides, 12 times sine of 25 degrees divided by 8. And it says round angles to the nearest degree and lengths to the nearest tenths. So I'm going to round this to the nearest degree. Whoops, not quite yet, because sine of A is the angle, but it's still stuck inside of a sine. So I'm going to I need to separate the angle from the sine. I need to take the inverse sine here. Angle A equals sine inverse of 12 times sine of 25 degrees divided by 8. Okay, now A is isolated. This is an angle measurement. Putting this into the calculator, we find that this is approximately 39 degrees. Okay, if we think about the graph of sine, right, the reason we're ending up with two triangles here is because sine inverse is limited. If you think back to when we talked about inverse functions at the end of last semester, we started out with a graph of sine, and then we reflect it over the line y equals x. And what we ended up with is a graph that was not a function. So we said, how do we turn this into a function? Well, we cut it off and we limited the inverse sine ability. But if we look at what angles will give us this value as sine, we can actually see that if I draw my angle of 39 degrees, the sine value, the y value on the unit circle, will happen again at 180 minus 39 degrees. So to find, this is a 1, to find a 2, I need to do a little bit of calculation outside of just using the calculator to do sine inverse. I have to say, what's the other angle that will have the same sine value? And that is 180 degrees minus 39 degrees. And that gives us 141 degrees. So our other angle here, A2, is 141 degrees. Now, I didn't know this ahead of time, but I can now see that my two diagrams are switched, right? Angle A1 is obtuse, angle A2 is acute. So I'm just going to go ahead and switch triangle 1 and triangle 2 so that the diagram makes more sense. So I'm going to call this A2 and this A1 instead, because that's what makes more sense with the diagram I drew. These diagrams, I called them 1 and 2 arbitrarily. I didn't know at the time which one would be obtuse and which one would be acute. This way it'll be a little bit easier as I find the rest of the values to make sure that they make sense. Okay, so we've got two angles and two sides. Let's go ahead and find the third angle here. To find the third angle, and let's do triangle 1 first, I have 180 minus 141 minus 25, giving me angle B1, 14 degrees. 1439, 180. So that's 14 degrees. And then in triangle 2, we have 180 minus 39 minus 25, giving me angle B2 at 116 degrees. Okay, so I've got three angles and two sides. I need the last angle. We'll use law of sines for that. So to find side, should we just finish triangle 1 first? B1, and I'll use a new color. So B1 divided by sine of angle B1, that's 14, equals, use the ones that were given. So the two that were given are C and C. So that's 8 divided by sine of 25, B1 equals 8 times sine of 14 degrees divided by sine of 25 degrees. And for side lengths, we're approximating to the tenths. And that tells me 4.58 rounds to 4.6. Same thing, but now for B2. So we have B2 divided by sine of angle B2, which is 116, equals the same ratio for our C's. So B2 equals 8 times sine of 116 degrees divided by sine of 25 degrees into the calculator and round to the nearest tenths is 17.0. Okay, so the trick with the ambiguous case is that if you're given one angle and two sides, and the angle is not between the two sides. So think about when we were doing congruent triangles back in geometry, we could not do the SSA case, right? Same thing goes here. The same reason that we couldn't do SSA for triangle congruence is because I could have created two triangles out of that information. So now we're going to look at calculation wise. If I'm given the SSA case, I can still create two triangles out of that given information. So now we can solve for both of them. If we're naming these, we would name this the acute because it has angle A is the acute angle. And we would name this our obtuse, angle A. Okay, we could name them backwards if we had been given side length B, then triangle 2 would be our obtuse angle B, and triangle 1 would be our acute angle B. So we can solve for just one of them, or we can solve for both of them, and I'll ask you for different things in different cases. Okay, that is the ambiguous case. So let's look at, this is the last slide, at an example of how we could apply this. This is used a lot of times in construction or like making roads or urban planning, things like that. So road slopes 15 degrees above the horizontal. So we have a horizontal line here. And 15 degrees above that, this is our road. And a vertical telephone pole, that's here, stands beside the road. The angle of elevation of the sun, that's represented here, so this would be the sun, is 65 degrees. The pole casts a 15-foot shadow downhill along the road. Find the height of the pole. Okay, so we have here our triangle. We know that the angle of elevation to the sun is 65 degrees. We know that the angle of elevation of the road is 15 degrees, but what we really need is some of those angles in the triangle. So if this angle of elevation, the 65 degrees, is to this parallel line, then we can use corresponding angles to say that the angle between the horizontal and the sun is also 65 degrees. So 65 minus 15 gives me 50 degrees inside of the triangle. To find another angle in the triangle here, we have that 65 degrees is not vertical with my triangle, it's vertical outside of my triangle. But I also have this 90-degree angle because we know that the pole stands vertically, right? So this is a 90 degrees, 65 degrees, and all three together make a straight angle. So I can take 180 minus 90 minus 65 gives me 25 degrees inside of my triangle. So if I'm looking at my triangle, I can call it ABC. Angle A is 25 degrees and angle C is 50 degrees. We also know that the shadow from the telephone pole goes from point B to point C, and that is 15 feet. We do not know the angle at B. Okay, so let's see if we can solve this. I gave myself a little bit more space here. So we have a 25-degree angle here. We have a 50-degree angle here. Let's find our last angle, angle B. is going to be 180 minus 50 minus 25, giving me an angle of 105. Okay, and now I want to find this side length. We could call it C, then this would be A. So I need to find C. Then I'm going to use angle C, sine of 50 degrees. And I want to find, or I have A and angle A. So that's 15 feet and angle A is sine of 25 degrees. Turns out we didn't need angle B. Never hurts to find it if you kind of want as much information as you have. So C or X, if I'm using my substitution property, equals multiply by sine of 50 degrees, 15 times sine of 50 degrees divided by sine of 25 degrees into the calculator, and we will round to 1 decimal place for length again, and we should get 27.2 feet. We did have units this time, so we have to use them. Okay, that's it for this section. If you have questions, feel free to email me. We'll go through a few practice in the next class.